2 minutes. Are people online able to hear me?
Yes.
Thanks, Sam. All right, let's go ahead and get started. Welcome to day 2 of the role of thunderstorms and tornadoes in wind engineering. We're going to sort of dig a little deeper on some topics that we mentioned yesterday. We're talking specifically about sort of design wind prediction, which will be some general discussion of how we do it, and then we'll turn our attention specifically to thunderstorm winds. And then we'll also talk about analytical models, which include both tornadoes and thunderstorms. And we'll actually talk about design wind prediction for tornadoes as well. But we'll also show that it's really done completely differently than most design wind prediction is done. For those of you who are registered in the class, I guess you guys specifically, there'll be a homework in the email. If you check the email from today, regarding the meeting, there should be a Dropbox link in there with all the information that you need. I didn't really set a due date or anything, but I would say within the next day or two, if you can get it to me by, what's the day, Tuesday? If you can get it to me by, let's say, Thursday morning, that would be good. And then those of you online as well, you should have access to the homework in there. And I would say by Thursday morning, Italy time, would be good. It shouldn't be too difficult. And they're in the folder. There's the homework document, and then there's some data as well in there, and then there's a couple MATLAB codes to help you run the analysis. So most of it should be in there. Any questions, just email me and we can sort through it. Generally, at least for today's homework will be topics that we cover today. Any questions before we get started? Okay, and if anybody has access or trouble with access to the homework stuff, let me know. Okay. Okay. All right, so let's go ahead and get started. Talking about first design wind prediction. So really an important component of how you compute design wind loads. And so that really sort of brings us back to one specific link in the wind load chain, which was the wind climate. And specifically, we'll talk about the extreme wind climate today. And so really analysis of the extreme wind climate is the basis for the wind maps that you see in various codes and standards. And maybe arguably, I would say it's probably not arguable at all, but really sort of the most crucial step in the wind load chain. Okay, so how you estimate the wind speeds, which are in loading then ultimately squared. Okay, so a poor prediction of your extreme wind speed, and then you square it. Okay, you can end up with large uncertainty and potentially large errors if you don't estimate it properly. Okay, one of the challenges with that, and we'll talk about this quite a bit today, is that we're really concerned with wind speeds with very low annual probabilities of occurrence. Okay, this varies from country to country. Okay, in the US, you're really talking about annual probabilities of occurrence on the order of 1 to 300, 1 to 700. So very, very low annual probabilities of occurrence, and we'll talk about some of the challenges with making those estimations today. Okay, and so really what we're going to do then is estimate wind speed values for specific return periods. Okay, and so we'll tie these two concepts together, annual probability of occurrence and return period. We'll tie those two together and show you how they link up. Okay, and so here is an example. Okay, from ASCE, again, ASCE 7. Okay, you have these sort of wind maps that are in here. This is the map that you see is for 700-year return period, okay, which is an annual probability of 1 over 700. And so the categories are an ASCE thing that's really kind of structure. It's related to the occupancy of the structure. So the higher the category, the more occupants there may be in there. So it requires sort of higher levels of importance or higher return periods that you need to design to. And so for each of these return periods, there are more in there, but there are more maps for more return periods. But for these particular 4 return periods, and this is for Champaign, Illinois. So you have 4 categories, you have 4 return periods, and then you have 4 wind speeds associated with it. Okay, so what we'll talk about too with extreme sort of design wind prediction and modeling is each of our sort of estimations or models are going to have these components. You have some frequency of occurrence, which is the return period. You have some intensity, which is the wind speed. And then generally you have some geographic location to go with it. In this case, it's a location in the US. Okay, so we'll talk about that, how that works for design wind prediction, but also how maybe tornado and thunderstorm models are a little bit different than what we've assumed. Okay, so we'll talk a little bit more about probability of occurrence. Okay, and in general, we're going to model these with some sort of probability distribution. Say most of you've taken like statistics course or something, right? I hope. Okay, so some of this should be familiar to you. And so generally what we're concerned with are 2 types of probability distributions when it comes to wind. One is the parent distribution, and then the other one is sort of the distribution of the extremes. Okay, so first let's briefly talk about sort of the parent probability distributions. Okay, in wind, usually we're talking about the mean wind speed value. So a lot of times parent probability distributions are used for 10-minute averages or 1-minute average, hourly average. So usually mean values, for example, if we're talking about wind energy, okay, typically what they would use is like a 10-minute mean wind speed, okay, and then they would fit a probability distribution to it. Usually those distributions are, you'll see like Weibull distributions used. Occasionally you'll see log normal distributions used. And really, I'm going to show an example of why sometimes it's hard to estimate the extremes. Okay, it's usually used for what I would say the bulk of the distributions. So really the center part of the distribution is where these probability distributions fit well. Okay, so these are the parent distributions. We'll talk a little bit more about that. Okay, almost all these sort of probability distribution fits, okay, are going to be based on observed data. Okay, so in your homework, you'll have a set of observed data. You're going to fit probability distributions to those. Okay, so here based on observed data, okay, and we're going to fit then to some continuous distribution. Okay, and so here, okay, so what we're going to do, talk about parent in the extreme, is, okay, so let's revisit, since everybody has good conceptual probability knowledge, let's revisit the concept of probability distributions. Okay, and mainly we're going to talk about the CDF, okay, which is the cumulative distribution function. Okay, and this basically is the probability that some random variable x, okay, is going to be less than or equal to some specific quantity. We'll say that's lowercase x. Okay, and in the CDF, this really means, okay, in layman's terms, okay, so this is really the probability of non-exceedance. Okay. And so then if this equals, okay, the probability of non-exceedance, okay, what's the probability then of exceedance? Right, so 1 minus probability of non-exceedance. Okay, so again, this is continuous distribution. Okay, and most distributions, okay, have some limits to them. So which values x can take. So in the Weibull, it goes from 0, okay, so it can't be negative. But then it goes to infinity, okay? So any extreme value in this distribution have some probability of exceedance, okay? No matter how small it is, okay, there's going to be some probability, non-zero probability, okay, of exceedance. And of course, we as engineers, for the most part, are interested in these extreme values. Okay. So, okay, before we get to truly extreme, so let's go take a look at the slides. Okay, so let's say here, look at the parent probability distributions. Kind of cut off there. Okay, so let's say these are distributions of daily mean wind speed over a 1-year period, right? So each day you collect a daily mean speed. Okay, you could bin it in some sort of histogram. Okay, and then you can fit some distribution to it. Okay, and let's say you don't know much yet. You say, let's say daily mean wind generally fits a Weibull distribution. So you fit a Weibull distribution to it. Now you can do, like in MATLAB, for example, there's just a simple function that gives you the parameters for these distributions. So you could say, give me a Weibull fit for this wind data, okay, and it'll give you the parameters. And so what you're seeing there in that PDF and CDF are the actual values, which are binned in histograms, and then sort of those solid lines there are the fits to the distribution. Okay, so let's say we fit these distributions. Okay, so if let's like we look at the Weibull distribution. So let's get in terms of wind speed now. So capital F of U, okay, so this is the CDF. So anytime you see the capital F, okay, this is U is wind speed. This is the CDF for the Weibull distribution, okay, which is 1 minus, okay, E, I write EXP here. okay, to the minus U over C to the W power. Okay, so here U is wind speed. Okay, and the Weibull distribution has two parameters of the distribution. So one is the shape parameter, okay, and this is W in this equation. Okay, and the other one is scale parameter, which is C in here. Okay, and then from our figure, our example on the slide, okay, we estimated that W equals 1.5 and C equals 6, okay? And so these are values in whatever unit your wind speed is in. So if your wind speed is miles per hour, miles per hour. Okay, so now, so we're interested in, again, high or really low values of probability of exceedance or high values of probability of non-exceedance. So let's say we're interested in, okay, before we start putting actual years and things to this, okay, let's say we're interested in the wind speed at the 99th percentile in this distribution, okay? So what would you do there? You would simply say, okay, I want the 99th percentile. The value of the CDF 99th percentile means 99% probability of non-exceedance. Okay, and so if you set F of U to 0.99, you plug in W and C, okay, you're going to get, okay, U equals 16.6. This is in meters per second, 16.6 meters per second. Okay, so 99th percentile, yeah, that's some pretty high probability of non-exceedance. Let's say we step it up one more. Let's say we're interested in the 99.9th percentile. Okay, so now the probability of non-exceedance is pretty high. Okay, small probability of exceedance. And if you did that, you would come up with 21.8 meters per second. All right, so now if you go back into the figure, okay, look at our observed data. Okay, let's look at the PDF. We say 99.9% probability of non-exceedance, 21.8 meters per second. What can you tell from our observed data in reference to that 21.8 meters per second? Exactly. We have not observed anything that high. Okay, so that's a key point. This is the challenge now in design wind prediction. It's not represented in the actual observations. So what are you doing? Well, you're essentially extrapolating out past the bounds of the available data that you have. So here, okay, example for these sort of high probabilities of non-exceedance, we are extrapolating beyond the bounds of the data and making a prediction about what that wind speed would be. Okay. And so for engineering purposes, for most things, we're interested in the high extremes. Okay, so for engineering, okay, we're going to be concerned with the extremes. Okay, for example, in the US, okay, one we're interested in return period, 700-year return period. Okay, we'll talk about that a little bit more and how we come up with that. And we're interested in, let's say, a 3-second gust wind speed. Okay, some other things we're concerned about as well with that. Okay, 700-year return period. Do you think that we have for a particular station in the US, weather station, do we have 700 years of data? No. right? So do not have 700 years of data. Okay. And so really there is considerable uncertainty. Okay, in what I'll call the tails of the distribution. Okay, so where that probability of exceedance is small, probability of non-exceedance is high, we don't really have any data out there to be able to tell us anything about what's going on at sort of those low probabilities. Okay, so to help with that, I'm not saying it fixes all the problems, but okay, we basically use the concept now of, okay, we'll turn to extreme value distributions and away from the parent distribution. Okay. Still not perfect. Okay. There's a couple different ones that we'll talk about today. Okay, but one mainly we'll talk about is sort of a three distributions sort of grouped together in one called the generalized extreme value distribution. Okay, so GEVD for short. Okay, and so these and really sort of most extreme value distributions, okay, are derived from the largest, okay, or smallest. You can do it on minimums too. Okay, value in a fixed sample. Okay, and so generally they'll call that an epoch. Okay. Okay, so an epoch then is just some equal division. It can be space as well, but here we're going to do some equal division of time. So anybody who's done the extreme value analysis of wind speed now, okay, will know what it is I'm talking about. So some equal division of time. Okay. And it doesn't matter what distribution it comes from. Okay. This distribution can be used for any of the any parent distribution. Doesn't matter what the distribution is for those observations. Okay, so the GEVD looks like this. So here, okay, capital F of X. Okay, so again, this is the CDF that we're talking about. Okay, so this is the CDF. Now here, X, okay, is going to be, in our case, will be wind speed. Okay, it can be any quantity. This particular GEVD has three parameters now. So we talked about the Weibull only has two. This has three. Okay, this one has the C parameter, which is called the shape parameter. Okay, this describes the behavior in the tail. A is called the scale parameter. This really sort of describes the dispersion in the distribution. And then U is the location parameter. Okay, and this really describes the central tendency of the distribution. Okay. Now, A and U are in the unit of interest. So here would be whatever the unit of wind speed is, and then C is a non-dimensional number. Now, the C, and we'll talk about it here in a second. Okay. Basically, you can split this distribution up into three based on the value of C. So as C approaches zero, okay, we'll derive this Gumbel distribution. Okay, you probably heard that if you've been in wind engineering. Okay, C is greater than zero is called Frechet. This also you might see called type 1. You might see this one called type 2. And then if C is less than 0, either called reverse Weibull or type 3. Now, as C approaches 0, okay, this distribution gets simpler. Okay. So now this is the Gumbel distribution, okay? And it's really used heavily in engineering. Okay, and we'll see why. We'll use it, and you use it in your homework to predict wind speeds for various return periods. So this one too, and these three have been a subject of debate. If you're familiar with sort of wind engineering, which distribution to use has kind of been a subject of debate in wind engineering, not as much over the last, I don't know, 15 years, but before that, okay, there was a lot of debate on what sort of distribution that you should use. And okay, maybe we'll see why. So okay, so here on the left, so here is the GEBD with the same A and U parameters, but a different C parameter. So this is wind speed versus f of x. So this is the CDF, right? Probability of non-exceedance. And what you can see is, well, yeah, they, for the sort of in the center of the distribution there, where the probability of exceedance and non-exceedance are close to each other, they pretty much line up on top of each other. But of course, in engineering, we're interested in the extremes out here, small probabilities of exceedance. Okay. Now, they look kind of close together. Okay. But if you zoom in on that, okay, for each of those types, okay, what can you see? So they kind of separate out a little bit, right? So let's say for the 99 percentile, right, 99% probability of non-exceedance, if you use type 3, it's over here. If you use type 2, okay, it's over here. That's a difference of what? 20, let's see, 80 to 9, that's over past 120 miles per hour, so 8 or 9 meters per second difference in which model you use. And again, if you square that, okay, those differences become magnified. Okay, so the key thing is, what's the best distribution to use when you likely don't have any data out at these low probabilities of exceedance? Okay. So, all right, so let's now sort of bring it back to practically how we're going to deal with something like this. Okay, as engineers, okay, we're concerned with both the frequency, that's going to be our return period or some probability, and intensity of what is really a rare event. Okay, and so to do that, okay, we need some estimate of likelihood or probability. In a given time period. Okay, typically in engineering and in wind engineering, usually that time period is 1 year. Okay, so we've been talking in sort of annual probability of occurrence. Okay, typically that time period, and you can do any time period, okay, is usually 1 year. And so basically what we're going to try to do then is estimate the likelihood that some event with some intensity will occur in this time period. Okay, and so how we generally do that is sort of each year then, if this is our time period of interest, okay, and we'll look at it as kind of a trial, how we're going to model it. So each year or trial is assumed independent of one another. And this is called a Bernoulli trial. Okay, and then the binomial distribution is used to model the likelihood. Okay, either, which is really sort of a binary type of distribution. It's either a success or a failure. Okay, and in our, we'll talk about it here in a second. Do we exceed or do we not exceed the value that we're concerned about? Okay, so let's give an example. So let's say we have some probability of success is at 2%, let's say per year, or really 2% per trial. Okay, so question then is, what is the expected number of trials before you have your first success? Okay, anybody want to take a guess what that is? If there's sort of a 2% chance of success on any given trial, what's the expected number of trials before you get your first success? Well, think about this. Let's say you have a coin that you flip, right? What's the expected number of trials before you expect to land on one side or the other? 50, yeah. So how many, so okay, so it's 50% you land on heads, let's say, in a coin. So how many trials, what's the expected number of trials before you would expect to get heads? Two, yeah, so two, right? So this then is sort of the expected number, okay, is just, if let's say our probability was 50% that time, okay, is just 1 over the probability of success, okay? So in this case, 1 over 0.2 is 0.02, sorry, is 50, okay? So 50 trials then is equivalent to 50 years. Okay, and so then this sort of mu is also known as what then? Return period, right? So this now is return period. Okay, R. Okay, so the expected, remember, and we'll talk about it, but return period then is sort of the expected length of time before you expect to see some exceedance of your event. And so you might also see it, ASC uses the term MRI, which is mean recurrence interval, which means the same thing. Okay, it's just another way of wording it. Okay, so now let's substitute R in for mu. Okay, 1 over P is return period. Okay, okay, we're here, where P then is what? Some probability of success, or we can say for exceedance. Okay, so then the return period equals 1 over, now, how do we get that back in a format that we've been talking about from the beginning? If P is probability of exceedance, okay, 1 minus P, right? And so 1 minus P, okay, where P now is the probability, or this is the probability of non-exceedance. Okay, so this brings us, this now is our CDF, right? So we can take this. We already know if we go back to some of these other notes, okay? For example, the Gumbel distribution, that's a CDF. So you could take this side of the equation and plug it down in here for your CDF, okay? So you can solve these return periods, okay, for different CDFs. If you rewrote this, you would say then the CDF, okay, is equal to 1 minus 1 over return period. Okay, so this is going to be important for how we do our probability distribution fitting here in a second. Okay, so let's do a quick example. We won't spend a lot of time on it. Okay, so let's say, again, we have this probability of success or exceedance at 2% per year. Okay, what is the chance or probability? Oops. That event occurs at least once in 50 years. Okay, so here really I'm asking the probability that X, which is our success, is going to be greater than or equal to 1 exceedance. Okay, and so this then is equal to 1 minus the probability of, okay, non-exceedance. Okay, so everything else, it doesn't matter 1, 2, 3, 4, 5. You can calculate the individual probabilities for those events. Okay, but here we're just looking if it at least has to occur once. And so probability of 0 is just then really, okay, 1 minus, okay, the probability of 1 minus P, which is the probability of non-exceedance, okay, for basically 50 trials. So if everything is assumed independent, okay, 1 year the probability of non-exceedance is 98%. Year 2, that probability is also 98%. So if they're independent, you multiply those two together to get, again, the probability of non-exceedance for 2 trials. Okay, if you did it for 50 years, okay, where this then again is our probability of non-exceedance. Okay, you get something like this. 1 minus, this is around 36%. Okay, so this is around 64% chance of occurring in a 50-year period. All right, so here, this is really telling us that 64% chance of occurring in 50 years. Okay. Which is pretty impressive if you think about it. You're talking about an event that has a 50-year return period, okay? It's likely that it's going to occur within that 50-year period, right? But everything is done on independent trials. Each year is independent from the next. So each year it has a 98% chance of not occurring, a 2% chance of occurring, okay? With that being said, let's say an event occurs in year 10, okay? Does it mean that it's not going to occur for another 50 years? No, right? So here, again, the probability of the next year is exactly the same, okay? Okay, so those are some general examples. Any questions on that from online or in class? Okay, so now let's turn to a practical application. Let's start looking at some real, actual data. Okay, so how are we going to do this in practice? So we're going to look at, oops, okay, where I live currently, where the University of Illinois is, Champaign, Illinois. Okay, we're going to look at data spanning from 1973 to 2019. Okay, the data is going to be 3 seconds averaging time, so 3-second gust. Okay, 10-meter height and open terrain. Okay, so standard conditions. Now, we're not going to talk really about standard wind speed standardization here, but that's a whole nother issue that can cause a lot of problems when you're trying to do this analysis. We're just going to assume that the standardization is perfect and the data is great. Okay. So here's what sort of this is, and you'll see here when I show the figure from Champagne, maybe. I don't know why it's doing this. Okay, so here's what the data from Champagne looks like. The gust data is, some of the gust data is thresholded, so it only records a certain type of wind gust if it's over a certain threshold, which is around 12 meters per second. Okay, so this is sort of every wind gust over that threshold in 46 years or so. Okay, so this is sort of what we have to work with initially. We have all this wind data. Okay, and so what you do, okay, to do the analysis, remember we said that we're using the extreme value distributions. Okay, you use specific blocks of time and you take either the maximum or the minimum in that block. So what we're going to do for this example for Champagne is we're going to take 1-year blocks and we're going to take the maximum wind speed from each of those blocks. Okay, so if we have 46 years of data, we're going to have 46 data points to use in the distribution. Okay. All right, so we're going to walk you through some steps, and then I'll have if I can share this screen here in a second, I'll show you sort of a MATLAB example, which you guys will have access to for your homework. Okay. Some steps to go through. Okay. Step 0, which we won't do, is standardize the data. Okay, again, typically we use sort of an averaging time of 3 seconds. In the US, it's different in different places. Canada uses nominally an hourly mean wind speed. Okay, Z naught is 0.3, so open terrain, and then the height is 10 meters. Okay, that's generally what's done sort of for codes and standards. You can standardize to any time, roughness, or height. The key thing is make sure everything is the same. You don't want to take a bunch of data that was recorded at 100 meters, group it together with data that was recorded at 10 meters, and then just fit the distribution without making sure everything is at the same height. Okay. Here, we're going to skip that and assume it's already done. Okay, and move on to step 1. Okay, and what we're going to do, and you'll see this in the MATLAB example, is rank the data and assign an empirical probability. Okay, so that's what we're going to do. So what we're going to do really is fit a CDF to our data set. Okay, we're going to assign an empirical probability. Okay. Okay, so cumulative probability, where the probability is equal to I over N plus 1. Okay, where I is the rank of the data. Okay, in this case, from smallest to largest. So I equals 1 is going to be the smallest value. Okay, so you're basically going to rank from smallest to largest. Okay, and you're going to give I equal 1 to the smallest, and then you're going to work your way up. And then N is, okay, the number of data points that you're going to use. Okay, so if you have 46 years of data, the number of data points is going to be 46. Okay. Okay, step 2 for our example is you're going to transform this probability okay, into Gumbel coordinates. Now this will make sense in just a second. Okay, so what you're going to do is you're going to take the probability from step one and you're going to transform it into this quantity y, which is the double negative natural log of the probability. Okay, and we'll discuss this here in a second. Okay, y sometimes is given the term reduced variate. Okay, and it's still probability. You're really just sort of transforming it into, and we'll see here, really just transforming it to better understand what's going on at very low probabilities of occurrence. Okay, step three then is just simply to plot our sort of ranked wind speed versus our reduced variate y. Okay, and so here, okay, I'll show that. This is for Champagne. So now we'll take the, we'll take the 46 annual maximum. Okay. And then we plot y, which is just the transform probability, and wind speed. Okay. So what does that look like to you? I mean, can we fit a line to that? Can we fit some sort of curve to that? What would you say? Yeah, could probably fit just a linear function to that. Probably be okay, right? Yeah. Okay. So, all right. So let's keep going further. Okay. So that looks like something maybe we can work with. We can model. Right now, we're just using the observations. Did I have another slide? Let's see. Hope I'm not giving anything away. No, let me show this one now. So that transform, so let's go back to our three extreme value distributions again. So here are our three CDFs for the different C values. One is C approaches zero, greater than zero, or less than zero. Now, if we do that transformation to the probability, okay, this is what it becomes. So now what do you see? So now we have the reduced variate here on the x-axis. We have our three distributions, okay? We can see in here where most of the data might be sitting, okay? They're pretty much on top of each other, but out here, for very low probabilities of exceedance, what happens? They all sort of diverge, right? And so in which of these distributions then seems like it might be the easiest to model? Gumbel, right? Yeah, so this one, yeah, that has a linear, basically has a linear function when you transform it to this reduced variate. Okay, and again, this is why it's fairly easy and common to use this sort of model in engineering extremes. Okay, so, and again, really sort of the reason to transform this probability is so you can see kind of what the tail behavior is. Like up here, this is what the tails look like if you just sort of plot it. This is probability now from 0 to 1, probability of non-exceedance. Oops. Okay, and now here, now you can get a much better idea of what's going on out in the tails, okay, which we mentioned is probably a big deal because again, we don't have data out there. We're talking very small probabilities of occurrence where there's no data. So the question is, what's the best way to extrapolate out past the bounds of the data? Statisticians would tell you, don't ever do it. You shouldn't do it at all, but we don't really have that luxury. So we have to do it somewhat. Okay, so at least I think the general consensus is, yes, we're going to use the Gumbel. Gumbel distribution seems like a good thing to use. Okay. So step 4. Okay, let's use Gumbel. Okay, we have two things now that we know. So the CDF of Gumbel, okay, we wrote down earlier. Okay, so this is the first equation that we're concerned about. This was our Gumbel CDF, but we also know, okay, the general form of the CDF, okay, at least for if we're assuming that 1 year is the trial, is equal to 1 minus 1 over return period. Okay, so that's our second equation. Okay, so now if we sort of set 1 and 2 equal to each other, okay, and we're going to solve for x, okay, it's a long derivation, so, and we got a lot to get to today, so I'm not going to go through it. So, but if you solve for x, what you find is that x, and again, x is wind speed in our case, is u plus a, okay, times the double negative natural log of now return period 1 over 1 minus r. Okay, and this part of the equation we said was our reduced variate y. Okay, so remember 1 over return period, 1 minus 1 over return period is a probability of non-exceedance. This one also, for the observed data, this p in step 2, also a probability of non-exceedance. Okay, and so then if you substitute y in for the double negative natural log, okay, what does that equation look like? A line, right? So now, okay, so we're at a line, much easier to model. Okay, we're now, u is our y-intercept, and a is the slope. Okay, so this is just sort of a linear least squares estimation, okay, for the Gumbel parameters, right? We have u, we have a. If we plug them back into equation 1, which we'll do in the MATLAB example, you can get a wind speed for a given return period. Okay, so there are other methods available too, if you're curious. Things like maximum likelihood, like if you do a Gumbel fit function in MATLAB, it'll give you the maximum likelihood parameters. Those parameters are going to be slightly different than what you get using least squares. Okay, ultimately, it's and we're going through this exercise, and hopefully we'll get to codes and we'll talk about this. But the key thing is the model is somewhat important, but the most important thing is that you have quality data, which is a lot harder than you'd think. If you don't have quality data, you know, it doesn't really matter what model you fit because, you know, your values are probably going to be wrong. Okay, so then the fifth step then is to fit the line, okay, this linear equation to the observed data that we just showed for Champagne to get your Gumbel parameters u and a. Okay, so for example, so this one in MATLAB, if you're curious, the function is EV fit, at least it was. You can use some different functions too to get your extreme value parameters. Okay, so all right, so let me stop sharing this screen and share my other screen. See if I can figure out how to do that. Okay, so let's see. So doesn't show up very well. Show well at all. Let me think. Oh, you know why? see. I guess probably people in class can, or people online can see it a little bit better. Let me see if I can figure out how to get rid of for you guys. Okay, that's not much better. We'll see if I can zoom in. Okay. And it's not important that we go through all the details here. Really, the key thing is just to kind of show what's in the code. You guys will have access to this. And so basically, in this, we're just going through the same steps that we just outlined in class. Okay, so you'll have this annual maximum data. You have the years. Okay, I'm really going to just plot a figure that shows each year and the corresponding annual maximum data point first. Okay, and then we'll just kind of go through each of the steps. So one is sorting the data and assigning an empirical probability. So that's this step here. That was that was like steps. Yeah, basically steps 1 and 2 there. Then to calculate the reduced variant, that's step 3. Then plotting, that's the figure I showed. So that's just simply plotting the reduced variant and the sorted wind speed. Okay, then here in MATLAB, you just estimate the parameters by least squares. So you just fit a line to that data. Okay, to get those parameters, this is some other things where I'm just sort of for plotting, listing different return periods that I'm interested in, calculating those probabilities of non-exceeds, and then transforming that probability for each of these return periods that I want on the graph. And then here, the key part is calculating the wind speeds for a given return period. So this is the last equation where the wind speed equals U plus A times Y. Okay, so these are param 0, 1, and 2 are the parameters of the double distribution. Okay, and then this last step, really, I'm just plotting everything together. So I'm plotting the values of the observed wind speed, and I'm plotting the values of the best fit. Okay, so let me run this. Hopefully it runs. I'll be able to show you a couple of figures. And this laptop isn't exactly powerful, so it may take a while just to do some simple stuff. So there's really what we want to see here, sort of just a plot of the annual maximum for each year. Okay, and then this figure then shows our best fit line fit through the data. So yeah, we were pretty accurate. We said, yeah, we could probably fit a line through that. It would be okay. It seems like it fits it okay. Okay. So now again, we have the observations here around 50 years of data. But of course, for design, we're extrapolating out past the bounds of the data out to these really high return periods, low probabilities of occurrence, right? So we're going to extrapolate out. We're going to pull these values for different return periods, and we're going to say, okay, this is our 700-year wind speed, for example. And this is in miles per hour, so probably around 50-ish meters per second, maybe a little bit less for 700 years at Champaign. Okay, any questions on that? In that Dropbox folder, the data for this one and the code is in there. You will have a homework assignment on something similar to this, but I'll make you think a little bit on it. Okay, so let me stop sharing here. Start sharing this screen again. Oh, I got a question from Mahmoud. Okay, so yeah, question from online says, after plotting the wind speed versus reduced variant, is there a specific test to tell which GV distribution to fit, or is it based on a visual assessment? Yeah, that's a great question. There are ways to test it. You can look at, like, you can just simply do sort of some optimization to any one of the distributions, a GEV distribution basically, to find out which one is the best. But in practical, sort of, practically what wind engineers have done is just said, we're fitting the Gumbel distribution no matter what. We don't care exactly how well the data fits, which is probably not a good thing. Champagne, the example I showed, is a really nice example that shows it fit fairly well. But that's not always the case. Does that make sense?
Yeah, it makes sense. I'm just asking because a lot of times they just go straight away with the Gumbel and then just fit the distribution without saying why. So,
Yeah. So, and we're going through this issue, and I'll talk about it. I'm developing the wind maps for ASC 728, so a new set. And basically, we're going to put some sort of goodness of fit criteria. We're going to use Gumbel, but we're going to put some goodness of fit criteria on it. If it doesn't fit well, like if R squared is below a certain value, we're not going to use the data. The advantage with the GEV though is that you can model that tail behavior better. Let's say that, instead of it looking like linear, let's say it looks like it sort of tapers off at the high end. So then you could add the third parameter, the shape or the tail parameter in there, and you would get a better fit. But yeah, so there's obviously ways that you can fit it. If you do GEV fit or something, it'll tell you basically what your tail parameter is. And if it's close enough to 0, you probably say, yeah, it's Gumbel. But yeah, there are obviously more hardcore tests that you could run to assess it.
okay, but the current ones are using the design maps are like mostly Gumbel, right? Like the current ones.
I'm sorry, Mahmoud, I didn't quite understand.
I'm saying the current ones using the design maps right now are mainly Gumbel, right?
They are Gumbel, yeah. Yep, exactly. And I will say with the current maps, there's no sort of consideration has really been given to if the data fits Gumbel well or not. But that's being changed in the next one, at least on some level.
Okay, thank you.
Okay,
Thank you.
thanks. Yep. Okay. So yeah, obviously there are going to be issues with the fits. Okay, there are other issues which we haven't really talked about. Okay, so we did our MATLAB example. Okay, we fit it. Oops. Okay, we did our fitting. Okay, we talked about how you would sort of then pick off your wind speeds for various return periods. Okay, and there's more steps to it, but again, this is how you would end up with your wind speed values in the maps. Okay, so you do this for a bunch of stations, you'd get the 700-year return period, and then there's some other mapping and smoothing steps that go into the final maps, but this in general is the process that works. Andy?
I have one question.
Sure.
To do this map, what distribution do you use?
So this is using Gumbel.
The Canada.
Yes. Yes. Okay. So yeah, so let's get into more specifics about kind of what was done for the maps. That's sort of the general process. Okay. What about some other considerations that we need to look at? Okay. Okay, maybe observations aren't always the best thing. So let's look at, this is a location in Texas. Okay, I kind of circled on the map where that is. The blue line is the observation, or the blue dots are the observations. The red line is the Gumbel best fit. And then the green line is the GEV best fit. And you can see that there's one data point up there, okay, at 130 miles per hour. Okay. Now, based on, I tried to show you a map where that location is. Now, what do you think? Any thoughts on what that wind speed may have come from? Exactly. So tropical cyclone, okay, so sits on the Gulf of Mexico, tropical cyclone. So if you used Gumbel or you use this sort of best fit GEV, you're probably not getting the right return period. So you can see if you use the best fit for 50 years, it's already up to like 200 miles per hour, 90 meters per second. Say probably not realistic. So one thing that we need to consider, well, let's get to a couple other things. Actually, let's not. Okay, so what else that's really important to this class haven't we really talked about yet? Okay. So with the hurricane example, that was a drastic example, are issues with the storm type itself. Okay, so everything that we've done at this point for Champagne, for example, what we did was just took the annual maximum speed. We didn't care where it came from. We fit a probability distribution to it. Okay. Now in reality, okay, storm types, whether it be thunderstorm, in this case, non-thunderstorm or hurricane, okay, different physical mechanisms, which we talked about yesterday a little bit, and turns out probabilities. Okay, so for example, which we won't talk about tropical cyclones that much, I mentioned it yesterday, that tropical cyclone wind speeds are completely modeled in the US. Okay, so don't use the observed data at all, mainly because there's just not a lot of it. A lot of times the tropical cyclone hits are relatively infrequent, and if they do hit, they damage the weather stations, and so you don't know exactly what the maximum wind speeds are. Okay, so as those things are modeled, they have different probability distributions than ABL winds say. Okay, so storm type here, different physical mechanisms and probabilities. So typically what we do, and I think probably some of you have done it here and online, okay, is generally what we do now is consider n independent mechanisms in a mixed, what I'll call mixed distribution. Okay. And so it's pretty commonplace now, but Gomes and Vickery way back 50 years ago were really the first ones to consider this, 1977 in Australia. It's pretty commonplace now. Okay. And so what we're going to do, how we're going to model that is we're going to say the probability now in wind speed, random variable V less than or equal to V is just going to equal the product. Okay. Now these are independent storm types. Okay. So for n different mechanisms, basically the individual probability distributions for n storm types. Okay. So now this is, okay, the probability of exceedance for all mechanisms. Okay, they're going to have different probabilities distribution. I'll show a couple examples. Okay, here in a second. Okay, so here, okay, so let's take a look at this. Go ahead and, yeah, go ahead. Sometimes I get ahead of myself. I just write the notes. Okay, so here's an example. Okay, going back to Gomes and Vickery. in Australia. And what they did was they basically separated out the storm types. E is extratropical cyclones and T is from thunderstorms. Okay, and then they fit separate Gumbel distributions to the data. Okay, and so what you can see from this one, and it's not clear which speeds belong to which storm, but okay, those probability distributions are different. So this is fit sort of the exact same way we just did the fitting for Champagne, where return period is transformed, okay, and then wind speed then is on the y-axis. And so you can see for a specific return period, okay, thunderstorms have higher predicted wind speeds than extratropical in this case. Okay, here's another example from the US, kind of showing the potential issues with sort of assuming or not assuming the difference in storm type. So this one's a little bit harder to read. So this is for a location in Texas. The blue dots are non-thunderstorm, the red are thunderstorm. The black dots are basically irrespective of storm type. So this is the exact same thing we just did with Champagne. We just took the annual maximum. We don't care what distribution it comes from. Okay, and then fit Gumbel distributions to each of those. Okay, and then the green line, which is sort of superimposed on the red line for a good chunk of the time, is the mixed distribution. So those the independent probability distributions multiplied by one another. So especially at the higher return periods in here. Okay, so if you're looking at 300, 700, 1700 years, okay, if you assume this black line, which was done before, you may be underestimating those wind speeds for high return periods, where sort of this green line is the mixed distribution. Okay, so generally this is pretty commonplace now where we're separating out the wind speeds based on storm type. Okay, and we probably should have got a little bit, and I don't have notes on it, but we probably should have talked a little bit more about how these storm types are classified in the observations. So in the US, at the weather stations, there are basically there's lightning detection systems for one. So if the system detects lightning, it will basically output that there's a thunderstorm occurring at the site. Okay, and you can use those thunderstorm flags then to classify the wind speeds associated around those times, classify those wind speeds as thunderstorms. In Italy and in Brazil, for some of the cases with the wind speeds in the ports network, and then in Brazil as well, they have anemometry, but they don't have anything to classify storm type necessarily. So a lot of times to classify speeds there, they used, does anybody remember here, it's like gust factor, right? Some sort of statistical metric to classify storms as belonging to thunderstorms or belonging to extratropical cyclones or something else entirely. So there's a few different ways to sort of classify those. In your homework assignment, they'll already be classified for you. There'll be a list of thunderstorm annual maximum. There'll be a list of non-thunderstorm annual maximum. And then you'll fit separate probability distributions to each, and then calculate the mixed distribution. Let's see. Okay. Any questions on that? All right. Okay, so yeah, and I will mention again, this is assuming that you have actual observations of the data. Okay, we'll talk about tornadoes. There really are no wind speed observations of tornadoes enough to use to do this sort of method. And so we'll talk about ways that we come up with return periods for tornado winds here. Hopefully we'll get to it today. Okay, so a couple other things to note about wind speed estimation. So in this example, we just use the annual maximum wind speeds. So for example, roughly we had 50 data points. Now there've been issues raised with sample size. And so there are a couple other methods that you can use to increase your sample size. Okay, one is to use what's called superstations. Okay, to kind of pool the data together. And so what you would basically assume is that you would take data from, let's say, 5 or 10 stations that were nearby each other. Okay, and group that data together. Say you thought it was in a homogeneous hazard climate. You pool all that data together, and then you fit a probability distribution to it. Okay, so for example, you can look at Turk and Shahid back in 1998 for how it was done for the US. Okay, another way that you can do it is to use subannual maximum. So there's a couple different methods in literature for that. So one is what's called the method of independent storms. The first publication on that was Cook and way back in 1982. There have been subsequent improvements to that method. Okay, there's another method that's called peaks over threshold. Okay, where you basically just as it sounds, where you would take wind speeds over a certain threshold, okay, and then fit a distribution to it, which we'll talk about in a second. And then you can just do something like, instead of annual maximum, you can just do, for example, end-day maximum. You could take the maximum wind speed every 4 days. You can take the maximum wind speed every month or something like that to get more data. The key thing there is that, if your epoch changes from 1 year, then then your probabilities then change. It's not annual probability of occurrence anymore. It's whatever time period that you're basically analyzing then. Okay, so just give you an example of how to do that. What time do we have? Like another hour or so. Get through all this. Okay, so let's talk about just a few things on subannual maximum. Okay, so here, let's talk about this method of independent storms. Okay, and I know there's been some changes since then, but in general, what Cook did was basically look at sort of long time histories of wind speed. And, wind speed would fluctuate over time periods. And he basically would say that when the wind speed got below a certain value, I think he called it like 5 meters per second. Okay, whenever sort of the wind speed dipped below these values, he would take the speeds in between that, and then he'd call this basically an independent storm. Okay, so this could be some arbitrary time period T in here. And so what then he would do is take the maximum wind speed from each of those independent storms and then fit a distribution to that data similar to what we've talked about before. Okay, and I think he did some sort of filtering too, where he sort of took some of the fluctuations out and sort of filtered over the top of it to get that. Or a simpler way, which is the end day maximum. We'll talk about peaks over threshold in a second too. So end day maximum is just what you think, right? So instead of what we did initially was just break things into 1 year blocks. Okay. Basically, we just sort of group things then even smaller into some end day window and take the maximum speeds there. Now, one potential issue with that is you're sort of adding a lot of wind data to the lower end of the distribution and not the extremes. The fits will look nicer, but I'm not sure. Does it help prediction? I don't know. I don't know the answer to that. So a key thing here too is, so this now, which I mentioned, so the return period is now measured. Let's say you did the end day period. Okay, and so N for extratropical cyclones, okay, generally I've seen around 1 to 4 days for that time period. And then for thunderstorms, I've seen anywhere from about like 1/8 of a day, so 3 hours to 1 day. Okay, so here, okay, just to cover the R, return period now is measured in end day periods. Okay. And so let's say, for example, now N is equal to 4 days. Okay, to get things into annual probability, which is probably where you want to be. Okay, so here is going to equal the probability of your end day values. So here, let's say 4 days. So you're roughly 91-ish events per year. Okay, so you have some rate now, which is going to be basically, okay, 365 over 4, which is around, let's say, around 91. Okay, so your annual probability is going to be the probability of your end day value to lambda. Okay, so you think about it similar to what we do for annual probabilities. You're going to take that probability for each year and multiply it together. You're going to do the same here, except now to get the annual probability, you're going to basically multiply that to the number of end periods you have. So you'll have 91-ish 4-day periods. Okay, to get the annual probability, then you're going to take those probabilities and take it to the lambda power. Okay, any questions on that? All right. Okay, I have a couple more slides to show, then we'll move on to the last hour. We'll at least start into windstorm modeling. Okay, here's another example of separating by windstorm type. So this is Champaign. Okay, so this was our initial example with that same data set. Okay, now and I showed this yesterday, black dots are for thunderstorm and gray are for non-thunderstorm here. And you can see that they belong to 2 separate probability distributions. Okay, and then the dotted line then is the mixed distribution. Okay, so you can get those wind speeds for various return periods. So we probably shouldn't have grouped everything together initially. Okay, but once you separate things out for storm type, the process works exactly the same. Okay, you'll fit your Gumbel distribution for your non-thunderstorm speeds, your thunderstorm speeds, and then you'll sort of multiply together to get this mixed distribution. Okay. Okay, here's an example of subannual maximum speed. So here's Champaign again. This is N just taking the maximum speed every 4-day period. Okay, you can see it fits really nice. But again, most of the data is back here in the lower speeds, which makes sense, right? So the fit looks good. If you compare it to, let's see, the 700-year speed there is around 100 miles per hour. If you did the annual maximum, of course, this is meters per second, but I think it was around 110 miles per hour. So there is a difference there if you're using subannual maximum versus annual maximum in the estimate. Okay, and it's really due to the fitting itself. Okay. One thing we haven't talked about since we're in Italy, now I feel safe talking about climate change. I might not feel safe about it in the US, but trends in the data. So thunderstorm and tornadoes specifically, if you look at, again, we did three things when we talked about the modeling here. Frequency, intensity, and location, right? The frequency is the return period, intensity is the magnitude at that return period, and the location here is geographic. For thunderstorms and tornadoes, okay, this is basically the confidence level for projections for climate change specifically are low for both of those, okay? So we basically, and it really comes down to the quality in understanding of, well, the quality of the data, the understanding of the data, and understanding how specifically climate effects would affect those small scale things. It's really sort of a scale mismatch from the climate modeling and then the storms themselves. Things get a little bit better when you talk about hurricanes. And then also talking about trends in the data. So generally we don't do it. So this is in the US. So this is over 100-year-ish period. Put this figure together a long time ago. The annual maximum speed over 100 years. And then each of these dots are different data sets because the data doesn't all exist in one place if you want to go way back. But what you can see is that there's a clear pronounced trend in that data. So when we fit these extreme value distributions, we assume that the data is basically stationary, that the properties don't change over time. Okay, here clearly they do. And a lot of it has to do with how the data were collected, what anemometer you're using, how the data was standardized. So there's a lot of other issues in the wind gust data. So it's difficult to make sort of projections on sort of climate effects versus just trying to understand the data quality itself. And it turns out the data quality, I think, is the most important. It's really hard to sort of sort out, especially when you're dealing with hundreds or thousands of stations. One station is not too bad, but when you're dealing with a lot, then it gets really difficult to be able to understand the potential reasons for these changes. Clearly on this one, there's a data set. The data sets just are different quality. They're different. You had to standardize them differently. Like this one, the blue dots were a 5-minute average that was converted to a 3-second gust. The red dots are already recorded at 3-second gust. Okay, so even if you standardize things to get things on a level playing field, then there's clearly issues with that. And we really talk about data standardization here, but always a consideration for when you're doing these sort of extreme value analysis work. Okay, so all right, so enough about extreme value analysis. That's one thing too. Next time I'll talk more about how the storms are actually classified in the data. Okay, so let's talk a little bit more about now windstorm models. Okay, but in general, that's what we just did, right? We developed a wind model, extreme wind model for a particular location. Okay, so talk about windstorm models. Sorry, question from online. Said how many years of data are usually sufficient to fit a GEV? I would say usually 15 to 20 years in general is probably good. The location parameter, like we talked about, the U parameter is generally pretty stable after about 15 years. Dispersion is not, but at least you can probably get a decent fit to a distribution after that time. Okay, windstorm models. Okay, we won't go too much background, but what we just did was we developed a model of frequency, intensity, and location, right? So for this location in Illinois, we had a frequency for return period. We had some intensity associated with that frequency, and then location. Okay. Okay, a challenge with this, especially when we're talking about sort of smaller scale windstorms, is that The data are measured at a single point, right? And maybe Andy will have on Friday, maybe talk about some of the challenges of trying to calibrate data that's collected at a single point to a sort of a footprint for a downburst, for example, right? So that's one of the challenges, right? And so everything that we've done up to this point, including the thunderstorm fits or extreme fits, is that, okay, we assume that the X and Y that the properties don't change. Over our building of interest, over our structure of interest, the properties of the wind don't really change, right? The only thing that changes is height. And when we took it at time, basically, we assume that things are independent of time, at least on smaller time scales. Obviously, we talked about a frequency, okay? But things like duration, okay, basically assume that things are independent of time. Okay, what we do know is that these other storm types, okay, that we're planning to focus on have different behavior. Okay, so now we'll have frequency, intensity, okay, location, and you notice too on sort of the climate change projections, this is sort of what they stuck with, sort of these three. Another thing that we'll add now is duration, right? These things are shorter lived, okay? We don't assume that these things are stationary or constant over an hour, for example. Okay, so we're going to add a couple things. So this one basically now, okay, anywhere I sort of put this asterisk, okay, this is something new that we haven't considered. Okay, so things like duration, okay, now things are going to vary in time. Location, we've kind of assumed up to this point that we're interested in geographic location. We still are. But also now we're going to interest really what I'll call sort of local location. Okay, now things will have some sort of footprint associated with them. Okay, so they have some smaller spatial dimension that we might need to consider. Okay, frequency and intensity for thunderstorm, we've already kind of done that, right? So this is, you can do it with observations, you can do it with the mixed distribution. Okay, tornadoes are going to be new. Okay, and how we're going to do that is going to be based on the damage that they cause. Okay, so we're going to use some sort of proxy for wind speed, proxy for frequency, proxy for intensity, okay, using damage. Okay, so one thing too, going back to our extreme wind models that we just covered. Okay, so these are collected, at least in the US, at weather stations. They're probably separated on average by, I don't know, 40 to 60 kilometers, or even more. Okay, in some places in the US, they have denser observation networks. So for example, this is Oklahoma, so this is in the center part of the US. The black dots are locations of the weather stations that we typically use for the wind maps. Okay, so these are usually at airports. They're, they've been around for a long time. The red dots are a smaller scale network of stations within the state of Oklahoma that's well maintained. You can sort of see how the density is quite a bit different. Okay, now one thing that will take us really to sort of thunderstorm footprints and really footprints of smaller scale events. So this figure is basically given a wind speed recorded at one of this smaller scale networks, what's the likelihood that the same wind speed is also collected at these weather stations that we use for the maps. Okay, so it turns out that, let's say, a wind speed of 45 meters per second is collected at one of these smaller scale weather stations. There's a very small chance that it's going to be captured at the stations we use for the wind maps. Okay, and so what that should tell you is that the footprint of these things are small. Okay, these stations have a much denser, the sort of the red stations here have a much denser footprint. And so these stations are able to capture much more extreme events. Now, what does that mean for our prediction of extreme winds? Are we doing it right? It's still an open question. But the key thing here to remind you is that these things have some small spatial scale. They occur at one station and they don't occur at the next station 10 kilometers downstream, or maybe they don't have as high as wind speed. Okay, so this is a real challenge. Okay, when using, again, like a single anemometer to try to measure the intensity of the event, because these things are going to vary in time and space. Okay. Okay, so let's look at a couple models for these. That's a great research topic, by the way. We haven't done enough on it, but yes, Andy.
One question. How do you manage to have it, to deal with,
I'm trying to remember now how we did it. It's been a while.
just stick on
Yeah, exactly. Yeah, so I think what we did was, yeah, I think basically we sort of made, there was some distance from the stations, right? And then I think we compared to see if there was a wind gust within some time frame and some magnitude of the one that was measured at the smaller network, right? So if one was measured at 40 meters per second at a smaller network, you'd have to find a comparable speed. I can't remember what the percentages were, but it had to be within a certain time frame and a certain magnitude. And so I think we compared across, yeah, I'm forgetting exactly how we did it now, but
Yeah.
it's in there, yeah, but yeah. So yeah, basically some geometric and time, some spatial and time scales. Good question, I'll look it up for you. Okay, so now let's talk about some more detailed models of extreme winds. So first we'll start with thunderstorm winds. Okay. And for now, we'll start with sort of the general model for downburst. Okay, and there are a number of models out there. Andy's had a few, at least one or two out there. Okay, and so now these models now are going to include intensity, okay, some maximum wind speed, okay, how things vary in all three dimensions, X, Y, and Z, okay, and they're going to have some time component as well. Okay, so now we're modeling a little bit more than what we did for design wind prediction. Okay, so generally, if we wanted to go full out with a model, sort of the frequency and location and intensity sometimes, okay, are going to be estimated from the observations. Okay, you generally know where these thunderstorm winds occur most often. Okay, so you know the geographic location, you know, even though the frequency is going to be debated because that figure I just showed, we're probably undercounting the frequency at the stations. Are generally estimated from observation. And the model then is really sort of based on what we talked a little bit about yesterday. Okay, so based on this sort of isolated downburst. Okay, so if you're looking at it kind of a plan view from the top down, okay, let's say this is your point of impact of our downburst. Remember, it hits the ground. We showed a video of that yesterday. Okay, so if you have this mass of air that's sinking to the ground and hits it, What do you think the wind direction is going to look like from the top down? Spreads out radially, right? So in general, so this is sort of the concept, right? So, okay, you have this downdraft impinges on the ground. Okay, and then you have this radial spread of the wind. Okay. So I'm going to introduce a simple model, and I think, yeah, I put that in your homework folder. There is no homework on the downburst one, but it's in there for you to play around with. Okay, the focus is going to be on one of the original ones, analytical model, Holmes and Oliver from 2000. Okay, so this is one of the original sort of analytical downburst models. Okay. Okay, Holmes's model accounts for horizontal or really radial velocity. Okay, it also has something to account for the decay of the downburst, well, both the enhancement and decay of the downburst over time. Okay. So now, okay, there are going to be models for wind speed and direction, right? So here's going to be a little bit different. And I should say too, going back to the design wind prediction, which I didn't write down. Okay, all what we did was essentially non-directional too. Each of those speeds have directions associated with them, but the maximum, typically the annual maximum analysis is independent of direction. You could do a separate directional analysis for the extremes. If provided you had the wind direction, you would do a separate extreme value analysis for each direction that you had. Okay, so, all right, so wind speed here. So now we're talking about some finite distance, right? So now we have our sort of center point here, okay? And we're going to describe things as some distance from the center point, which we'll call x. Okay, so x here is distance from the center. Okay, and we're going to basically describe the radial component of the wind speed as a function of this distance. Okay, and so, and maybe, I don't know, Andy will talk about maybe the advancements in some of these models on Friday. Okay, but generally here, okay, we're going to have radial wind speed now versus distance x. Okay, I'm going to split things into two separate regions. Okay, so one region is going to be sort of near the center. Okay, so if this is sort of the center point here, just say that's 0. Okay, we're going to split things into two regions, region 1 and region 2. Okay, where here is our maximum radial speed. Okay, and here is what we'll call R max, which is the radius of maximum winds. Okay, so here R max, now this is an important parameter because this is in everything. So this is in tornado, this is in the tornado models, this is in the downburst models. Okay, so some radius of maximum wind. Okay, Holmes also has some length scale in here, which he calls capital R. And this is about 1/2 of R max. Okay, so we have this sort of sort of linear increase, and it has some intuitive sense, right? You kind of see a downburst. If you're looking at sort of the horizontal speed near the ground, you would expect it to be close to 0 near the impingement point where the flow is sort of all up and down. And then you have the spreading out where the flow then increases to a maximum and then decays out past the radius of maximum winds. Okay, so we have these two areas that were considered, and even tornado models really follow sort of the same logic. Okay, so we have in this region 1, which we're going to say is inside the radius of maximum winds. So here, where x is less than r max, okay, this radial speed is then going to be equal to VR max, okay, which is then just going to be modified by this sort of non-dimensional distance, which is the distance x over r max. Okay, and then the second region is going to be then outside r max, and we'll also include r max itself in here. So where x now is greater than or equal to r max, okay, we're going to have VR is going to be equal to VR max times, we have some exponential function here for the decay. Let's see if I can get this right. I've written this wrong in the past. X minus R max over this sort of length scale that he has, R squared. Okay, and so again, this is generally how the extreme wind models work. Basically, you have one function that describes the behavior inside the radius of maximum wind, and then a function that describes the behavior outside the radius of maximum wind. Okay, another thing that he has, which I mentioned, is okay, something that handles the duration. Okay, so where you think this downburst generates itself, it comes to a maximum intensity and then it starts to decay after some period of time. So here he has VR equal V max times, here again exponential. Now this is going to be related to some time function minus T over T times, again, this sort of normalized distance between your location X and the radius of maximum wind. And then in 2, VR is going to equal, okay, these two are the same. And then here is going to be your exponential decay. Okay, so now we have time parameters that we need to consider, where T equals the time from peak intensity and then this T here is some time constant, which he based, I don't remember what the exact value was. Okay, it's based on measured data, and Holmes basically used a single case to estimate what that time constant was. And so here, so at VR max, the time is 0. So once it reaches its peak intensity, that time is 0. Time is measured from that time of the peak intensity. Okay, so here, this describes, well, these things describe two things: the wind speed radially, and then how that wind speed changes in time. Okay. The next thing that we'll do that we really haven't done up to this point is estimate now the wind direction associated with that wind speed. Okay. And in general, for this radially spreading downburst, it seems pretty easy, right? So if this is our center point, okay, you're interested in some location up here, okay, that direction, that vector is going to look something like that, right? Okay, so that's relatively easy on the direction side. Okay, one thing we haven't talked about too is, again, this assumes that things are, this downburst stationary, the storm's not moving, it hits the ground, spreads out radially. Well, okay, to complicate things maybe a little more, okay, is that these storms also translate. Okay, so they move in space, right? This whole thing, this storm is moving along in space. Okay, so it has some translation velocity associated with it. Okay, so kind of give you a cross-sectional view. So let's say you have this downburst. Okay, it hits the ground and spreads out. Okay, one goes, okay, one vector goes one way, one goes the other way. Let's say now, okay, this is also translating at some velocity, right? So if you look at these two cases, okay, if you sort of add those speeds together, let's say these are equal, okay, so things, we're assuming that things are axisymmetric, that they don't change only with radius. Okay, we have this vector. Now, basically, we're going to add the translation vector to that. And on this side, okay, the translation vector, if it's dotted, we should have did the dotted line here. Okay. The translation vector then opposes this vector on the other side. So when you add them together, and that's, again, a subject of debate, does it just sort of linearly add up to translation? In tornadoes, it clearly doesn't, and we'll talk about that. This vector then becomes smaller. Okay, so you're subtracting, you're really sort of adding the translation speed. It's additive here, it's subtractive here. So on one side, okay, you may have higher speeds than on the other as this storm translates. And so for direction then, okay, for this location, let's say again, okay, we have this radial component. We're also going to have some translation speed, okay, some translation vector. Okay, and then you're just doing vector addition here to get the total wind speed. Okay. So in this case, the translation vector both increases the wind speed and changes the direction associated with that. Okay, and if you think about translation, sometimes it's kind of hard to visualize. Sort of imagine like two people movers, like at the airport or something, you know, sort of the belts that carry you across. Okay, it's moving at some speed. If you're walking at some speed along with it, okay, that's additive. Your velocity is the speed of the belt plus your own walking speed. If you oppose that, if you oppose the motion of the belt, okay, you're going to get slowed down because that sort of is opposing your motion. Okay, and so you have to if you're walking at the same speed on either side. Okay, and so it is a real thing. Sometimes it's hard to conceptualize how that works, but we've definitely seen the effects of translation speed, and at least in damage, where it's clear on the side that the tornado, for this as example, is translating. There's quite a bit more damage on the side where there's translation. Okay, so let me show a couple figures, and then we'll ask questions about it. So downburst model, again, there's a lot of variations now. There's a lot of models out, and I should say that I will get to that. So here's sort of a dramatic example of what that sort of downburst might look like. Okay, and so what you can do, so this is from Holmes's paper. This is the model. So what you can do, and you'll have to do in your homework for tornadoes, is generate a time history of wind speed and direction for a particular point. Okay, and so what you can do using these models of wind speed and direction is you can get the wind speed, time history over time, and he's going backwards here, so time is right to left here. And then changes in direction associated with that time. Okay, another thing that you can get from this model is a footprint of maximum wind speeds. Okay, so this is really unlike other things that we've done. We've just sort of fit a wind speed, extreme wind speed model. We get a wind speed. We don't have any dimensions associated with that. Okay, so here you can develop, and based on some sort of the parameters in the model, you can generate these footprints. So this is an example of like the maximum wind speed over in some space. Okay, and you can see here the direction is right to left, and so those speeds extend out in the direction of translation. Okay, so if you imagine maybe, I don't know where the center point would be, maybe somewhere back here. Okay, translation is in this direction. Okay, things are radially spreading out. The maximum effect of that translation is going to be right here in the center, where that radial vector is in the same direction as the translation. Okay. Now in your homework, in the shared drive, okay, I have a simple downburst model from Holmes. One thing I didn't include is any sort of time decay. So basically you assume that it's steady state. Okay, and so for example, this is a snapshot in time, or basically unchanged downburst model. Okay, with some parameters. Okay, I think you can figure out the direction of translation is here, there, and you can kind of see what those wind speeds look like in time. And you can see sort of how small that footprint is here. I think the footprint is just a couple of hundred meters, and the extremes are very similar to that, just a couple of hundred meters in dimension. Okay, so there is MATLAB code with a model like that, so you can play around with that and look at what these sort of downburst models look like. They do include translation, and we'll come back to translation here in a second. Just so you can see how to, if you play around with the parameters, what will happen to the wind speed footprint. Okay, any questions on that? Okay, so that's a fairly simple model. Give you an idea of what that looks like. One thing we don't have in the Holmes model, and I don't, Andy, did you add vertical profiles or no? Working on it. Okay, so so we'll say this. We'll say no. Well, we'll just say this. So there's no model of vertical profiles in Holmes and Oliver. Okay, so we do know on some level that these profiles vary vertically. They're not ABL-like. Okay, at least at some height. Okay, so there's no model of vertical profiles in Holmes and Oliver. Okay, but if you think about it, just again, intuitively, right? So if this is height, let's say again, some cross-section of our downburst, say this is height and this is some distance X, you have the wind speeds hitting the ground, spreading out, something like this. Maybe you get some ring vortex or something here. Okay, what would you expect if I was to draw then a vertical profile of the wind speeds, vertical profile of the horizontal winds? What would you expect that profile to look like? Yep. So yeah, so think about it too. Yeah, verticals would definitely change like that. What if we were considering just the horizontal component of the wind? Yes. How would you think that would look? Yeah. So maybe it might look something, yeah, exactly. So higher in the ground and then sort of decaying as it goes up, right? So here, okay, you might expect a vertical profile to look like this, where now this is some profile with Z. Okay, quite a bit different than the ABL, which we showed is just monotonically increasing. Okay, so there are some out there. I'll show a simple one from Wood, 2001. So this is a normalized profile. So UZ normalized to the maximum wind speed. I have a bunch of coefficients in here. Okay, which I'll describe. So A times Z over Z star to the B power. 1 minus, is that the error function? I can't remember what that is. C Z over Z star. Okay, so this is from Wood in 2001. Okay, so this is when sort of downburst research was starting to gain traction in wind engineering. So there's coefficients there, but generally in Wood's paper, they just assign constants to these, where A, B, and C are all given values, and then Z star is the height where U is equal to 1/2 U max. And I think estimated that around 6 times the height of the maximum wind speed, okay, which would be in here, let's say. Okay, so this height would be Z max. Okay, so again, there are a lot of models out there. Just recently published as sort of a comprehensive list of existing ones. And I think there's MATLAB code that goes along with it if you're interested. So this is Britton and Romanich 2026. I think there's at least 9 sort of downburst models in there. Some that are I think some are 2D, some are 3D. Obviously, some have time components and some don't. But it's a good idea to see sort of what's out there as far as downburst models go. Okay, so a couple other things on downbursts, and then we'll move to tornadoes. And we may or may not finish it up. If we go, are you guys okay to go till 6 if we go there? I'm only obligated to do 12 total hours. So if we go 3, then we can shorten it up another day in class. Okay. There are other sort of frameworks, and we'll show some slides too. There's sort of other frameworks that exist to model sort of these non-stationary downburst winds. Okay, one was by Solari in 2016. So this was the thunderstorm response spectrum paper. Okay, and so really there are a number of sort of empirical functions that you can use to simulate how these things vary in time and space. So for example, there's functions to describe how the mean wind speed varies in time. Things like the turbulence intensity varies in time. So here, again, these functions in the ABL are assumed not to vary in time. These things actually vary in time. Okay, so for example, this sort of time varying mean is equal to some actual wind speed time history plus a fluctuating, wait, let's get screwed up here. Yeah, so the wind speed at time t is equal to some time varying mean wind speed plus some fluctuating component, which also varies. Also, there are some other non-dimensional functions like beta and alpha, okay, which describe sort of the behavior of the mean wind speed and the turbulence intensity with height and also over time. So these are really sort of how to deal with things like the profile shape, okay, and how those things change in time. Okay, but the bottom line is, and I think sort of maybe Andy will agree, we don't have great information on things like footprints of the storm. Okay, and things like correlations in the wind field for these events. Okay, if you go back and look at the Holmes model, okay, he based everything on really a single event. which is really so far out of the sort of what I would consider typical downburst, I'm not even sure how representative it is of what's going on. So if you're curious, this is from Andrews Air Force Base in the US in the 1980s. Basically all the information that Holmes used in that model from the field is based on that single event. That probably could use some looking at and potentially people already have.
Anche per la fila parallela c'è più l'effetto protettivo, si genera uno scavo che è anche superiore rispetto a quello nel senso di fondazione, così come inclinandola a 15 gradi.
Okay, there we go. I don't think you're talking to me. No.
Yeah, you,
What? Yeah.
we just need. When it's finished.
Yeah. Okay, so. Okay, the information that we do have. Show considerable variability. Okay, so there's just, in the thunderstorm information we do have, there's maybe not a consensus on how things actually behave, or do we have enough information to understand how things behave to develop really robust models. Okay, so show you an example. So this one is this is the wood profile for different cases. When it's normalized, all those profiles tend to collapse on one another. I think there's a couple different cases from a couple different studies. But really what I wanted to show is sort of the variability in observations. Okay, so this was the one on the top left is from one of Solari's students, I think, back in 2016. So this is a normalized function of wind speed in thunderstorm events. And so the black line is sort of an average where 1 is the peak and everything's normalized to the time and the peak wind speed. So everything sort of collapses at t equals 0 seconds. And this gamma, which is just a ratio of the maximum wind speed to the wind speed at a given time. Okay, a ton of variability here. I mean, so much variability, it's even hard to really understand what's going on there. And the black line is then the average of all that. And then another one, this is for a paper that should be coming out pretty soon. This is for thunderstorm profiles in the US. Really what I want to focus on is the black and gray lines here. So these are from the actual observations. One is averaged at 3 seconds. The other one is averaged at 30 seconds. Look at the shape of the profile. And it does sort of look log-like up until a certain level, but also sort of the here you can see plus or minus 1 standard deviation in the profile. So there's just there's still just a lot of variability there in sort of the shape of the profile. Even on average though, these are ABL profiles and ASE. So these are the gust profiles that they have in there. There's some similarity there, but still a lot of variability in the thunderstorm profiles. Okay, so there is, so kind of moving slightly away from sort of the isolated downburst, there is some attention being paid to what I mentioned yesterday, these sort of large scale thunderstorm systems. So a lot of times they're called mesoscale convective systems or MCS. Okay, so things like the derecho are included in this. And so these sort of thunderstorm events are responsible for the highest extremes in some locations. Okay, and so I'll show you a couple examples of that. from one here in Europe and then the other one in the US. So the first one is this time history. It's kind of hard to read here. This is from the Corsica derecho in August 2022, which I think also came through Genoa. Yeah. So this was a pretty significant event. And now I'm thinking, okay, I see. The blue, let's see. No, the black line is wind speed in knots. So here in this case, the knots, like roughly a meter per second is like 1 knot is like half a meter per second. So for this one here, 50 meters per second peak wind speeds for this particular case that hit Corsica and hit other parts of Europe, including Italy. And again, these are scale. You can see here, this one is the one this was in the US. This one has a fairly large scale, 1.5, 2 degrees latitude from north to south. So large spatial scale. And here's sort of the estimated map of the peak wind speeds from this case. So this is in miles per hour. So estimated 50, 55 meters per second peak winds in this particular case. And also you can see just how large the spatial extent of the extreme winds were. So hundreds of kilometers sort of in the direction that the storm translated. Okay. So the question is too, do wind engineers need to take notice of these events? That's an open question, I think, and hopefully we'll talk a little bit more about it when we talk about some of the state of the art work that's going on in thunderstorms and tornadoes. Okay. Any questions on that? Or thoughts? All right. Can you guys handle another 45 minutes or no? You guys want to call it a day? Good? Okay. Okay. We'll push through. Okay. We'll move to tornadoes. Maybe we'll cut the lecture short tomorrow. Okay, so let's move to tornado models. Okay, so let's talk about some of these parameters that we talked about elsewhere. Okay, we've mentioned it before. Very few or no actual observed measurements of tornadoes. There are a few, but not enough to develop any sort of models. Okay, so you can see what all the rest of these sort of parameters that we're interested in are estimated from. Okay, the frequency, we're going to estimate it from damage. Intensity, also estimated from damage. The location, damage. Geographic and spatial location, at least partially estimated from damage. And then the duration, also partially estimated from damage. Okay, so you can see now sort of the problem changes. The problem changes significantly when we talk about tornadoes. Again, much smaller scale than even downbursts. And so unlikely to get any measurements. So the best way to do it is based on damage. Okay. Now, there are some significant issues with that, and we'll talk about those. Okay, so here first we'll talk about the two biggies. Okay, frequency and intensity. Okay, how often do these things happen and at what intensity is associated with the frequency? Okay, we already mentioned that these are damage-based estimates. Okay, and in the US, Okay. We use the enhanced Fujita scale or EF scale. Now in Europe, they use the IF, right? International Fujita scale, which is different. Okay. Either way, both of the Fujita going back to the EF scale, back to the F scale even, EF scale especially based on what we call expert elicitation. So not necessarily a lot of science backing the estimates for the reasons that we talked about previously, where at least for the EF scale, we get a bunch of people in the room and say, what wind speeds do you think would cause this particular damage? And then it's so decreed. IF, yeah. So this is what we're dealing with, right? So you can see already, and we'll talk about maybe some science-based ways that we're trying to get at some of these things, but potential issues with frequency and testing estimates based on damage. Okay. And to give you an example, so in the US, and there's a large database of tornadoes in there that you can use to do estimates, is what you'll find is something like this. So let's say, and we'll talk about these ratings. So let's say this is what we'll call an EF5 tornado. Okay, so we'll talk about what the EF5 means and the wind speeds associated with that. Okay, so what's in the database? You'll see this. You'll see the rating. You'll say, okay, this is an EF5 tornado. You'll have, okay, the path length. Okay, so this is really just based on damage. Okay, here you'll have a maximum path width. Okay. You'll have a start point, which is just sort of the center here of the beginning. Okay, and then you'll have some ending point. Okay. Anybody see any potential problems with this? So this is what the database essentially comes with. You have the length, maximum path width, start point, and end point, and the rating. Now, again, a couple things. Okay. This is damage based. Okay, what happens if there's nothing around to damage? Yeah, probably doesn't get a rating. Okay. What happens if, well, we'll talk about tornado models, but there's a house out here that takes some damage. It probably wasn't near the highest winds, but that's the only structure they have to rate. And so that's what the tornado gets rated. Okay, so there's some issues with that. Okay, and I'll show you some examples. Let's talk about the EF scale first. Okay, the enhanced Fujita scale, it's about 20-ish years old now. And I will talk about some changes that are going to happen to the EF scale. Okay, but again, what it is just sort of a method, a scale to estimate wind speeds from damage. Okay, and so what happens, we'll kind of work from end to beginning here. So what the EF scale is essentially is it relates the EF number to specific estimated wind speed value. So EF0 to EF5, then the 3-second gust speed, this is in miles per hour. EF0 is sort of the weakest tornado, 65 to 85 miles per hour. So that's like 26 to 34 meters per second or something like that, all the way to EF5, which is greater than 200 miles per hour or 90-ish meters per second. Okay, so each of these numbers, the rating represents an intensity. Okay, so that goes back to our frequency and intensity discussion. Now, how you come up with those numbers are, and it says here, okay, there are 28 damage indicators. And so each damage indicator, for example, these are 1 and 2 family residences. So basically single family homes in the US. Okay, a lot of discussion about that. Italians don't understand, Europeans don't understand why all our houses are made of wood in the US. But this is primarily what it represents here in the EF scale, are light wood framed homes. Okay. And so this is damage indicator number 2. And so what you see for each damage indicator are a number of degrees of damage. Okay, and that's on the left-hand side there. So degree of damage 1, that's like the threshold of visible damage. So you might see like a piece of siding or shingle or something off the roof, for example. And then DOD 10 is the destruction of the residence, or complete destruction, where the house is not even, there's no even sign that the house was even there. Okay, and so that's the highest degree of damage. Now, the 3 right columns then show basically sort of 3 wind speeds. So these are all wind speeds, the farthest 3 columns. The expected is sort of for typical, the assumption is for typical construction. These are the estimated wind speeds that you would get. So if you saw, for example, that your exterior walls were collapsed, which is DOD 7, the expected, and you said this was a typical construction house in the US, you would say, okay, 132 miles per hour is what would have caused that. Now, there are these lower bound and upper bound speeds, and that's really to account for construction quality, which can vary quite a bit. But a lot of times this sort of expected wind speed is used there on the left-hand column. Okay, another problem with sort of assuming this rectangular shape in the damage is that, well, tornadoes don't really necessarily behave like that. Okay, so this is sort of a damage map from a tornado in Oklahoma, which is a tornado-prone region in the center of the US, where you can see it changes direction quite a bit. It also, the intensity changes quite a bit. So you can see where the width of damage shrinks as the tornado moves along, the intensity shifts, at least based on damage, of course. And so, you know, tornadoes are just sort of rapidly changing in time and space. And so maybe the damage models aren't necessarily the best to handle it.
Do you have an idea what causes the directional change in the trajectory of the tornado?
A little bit. So most thought is that there are sort of, remember the video I showed yesterday, right? With some of these subvortices and things that pop up. That's part of it. That's the thought, that maybe these sort of localized vortices pop up and you get sort of the center of damage is displaced. And so it looks like things shift. So basically, and in this case, this is a pretty unique case here where basically the tornado did a loop. It basically did this and continued on. There's some speculation on why that occurs, but I think the thought is sort of, again, really sort of tornado specific interaction with the surface, what's going on. This was a heavily populated area. So the thought is, and a couple things too, just sort of with interaction with the surface. Also, there is some thought that sort of how tornadoes, we won't go into it, but tornadoes tend to cycle sometimes. Basically, sort of the initial vorticity, then the tornado occludes and a new sort of vorticity source pops up. And this can cause this sort of change in trajectory. So there's a couple potential reasons for it. This one was really unique in the sense that it sort of did a loop on itself and then sort of continued on in a whole new direction.
How is it linked, for instance, if storm is moving in one direction?
Yes, yeah, because the storm, so the storm in general, I don't know exactly which way the storm, but I don't think it's not a change in the storm direction. It's really a change in the tornado direction. So here, the storm direction probably just went like that. But sort of location of the tornado underneath that storm, or the strongest intensity, changed. Yeah, that's a good question. And I don't, it's not solved, I would say. Okay, so okay, there is a database that exists. We won't do, I don't think, any homework or exercises on it. Maybe if I do this class a second time, we will. If you go to what's called the Storm Prediction Center in the US, okay, they have the entire sort of US database, tornado database. Okay, and this database is used to estimate things like frequency, and intensity. Okay, and so we'll talk about basically two methods that are used, how we're going to use the tornado database to estimate frequency intensity at a particular location. Okay. So typically what happens, there are going to be two cases. Okay, the first one, which I guess we'll do in black. Okay, it's going to be what we'll call point-based estimate. So this is just for a particular point in space. And then the second one we'll call spatially based estimate. Okay, and they both basically work the same way. Okay, the one difference is spatially based estimates are going to be used for large structures or large areas that you need to consider worried about getting hit by a tornado. Okay. So the assumption that you're going to make to start is that you are in a homogeneous hazard region. Okay, so basically you're going to choose a region that you think has the same hazard properties, right? So in the US, like Oklahoma or something like that, or Kansas or Texas, areas of those, you could say maybe they have a homogeneous hazard region. You wouldn't compare it to you wouldn't sort of do group Oklahoma and California in the same region, okay? So you're going to have some homogeneous hazard region. Okay, we're going to call this some area of the region. Let's say this is 1,000 square kilometers. Okay. Now, using some tornado database, okay, what you're going to do is you're basically going to have all these different tornado paths that exist in that region. Okay. Okay, so these are, again, tornado damage paths. Okay, and also let's say that you have some time period that you've analyzed this data. So let's say you have 50 years of data. Okay, and over 50 years, you have all these different tornado paths. Okay. Okay, and so let's say, for example, this particular tornado is an EF2. Okay, so if you sort of zoom out, you have your tornado path here. And so within this EF2 tornado, okay, basically not the entire tornado has EF2 winds is the assumption, right? So you have, and maybe I should make this a little bit larger to kind of show it. Okay, so let's say this is our path. Okay, the winds are going to vary in space. So let's say here you have sort of EF0 winds on the outskirts, EF1, and then EF2. Okay, now you'll see when we do tornado models, which is very similar to downburst model. Okay, so near sort of at the radius of maximum winds, it has some maximum intensity and then it decays as it moves away. Okay. So these sort of proportions of wind speed, okay, are based on damage in part, okay, and the second are based on what's called a Rankine vortex, okay, which we'll cover next, okay, which is a simple tornado model. So how these wind speeds vary in space, okay, are going to be based on these two things. Okay, so for each of these methods are so for each of this EF2 tornado, some proportion of the tornado is going to have EF2 winds, some proportion EF1, and some EF0. Okay, so I'll show you an example of that in one publication. Well, here's an example. Okay, here's an example of EF2 or basically a density of EF2 or greater tornadoes in the US over a 30-year period ending in 2011. But really that area hasn't changed. So anywhere sort of east of the Rocky Mountains is a tornado prone region in the US. Now, these estimates, so there are a couple different studies that were done. This is one by the nuclear industry in the US. So for example, okay, and this is F2, but nothing has changed between EF and F2. So for example, this is the recorded tornado F or EF scale. So for an EF2 or F2 tornado, 11% of that area is going to be EF2 winds, 27-ish% is going to be EF1, and then 61.6% is going to be EF0. So for each tornado area, there's going to be a subset of that area that has wind speeds of a certain intensity. Okay. So how this works for the point-based method is really pretty easy. Okay, so if you're looking for some return period for some EF number, okay, it's really just going to be the sum of the area for whatever EF category you're interested in over your region area times the time duration that you've collected the data, all to the -1. Okay, so let's say, and this is just a hypothetical, let's say that the area of EF2 wind speeds is equal to 18 square kilometers over this 50-year period, okay, in this homogeneous hazard region. Okay, so if you did this calculation, this would be 18, okay, this would be 1,000 square kilometers. This would be 50 years. And if you do that, you'll get sort of a return period, and this is about 2,800 years. Okay. So really what this method does, and I'll just sort of write it down here. Okay, so this is basically the expected amount of time that you would have to expect this whole homogeneous region area covered by EF2 winds. Okay, so in 50 years, some proportion of this 1,000 kilometer squared area has been covered with EF2 winds. Basically, then you're just sort of extrapolating that out to in how many years will this entire area be covered, assuming that occurrence within this area is random and uniform. Okay, so that's a pretty simple way to do it. Of course, there are potential issues with the area estimation and things like that. Most places in the US, if you do this method, like even the tornado prone regions, I think are like usually around 10, even the most like for EF2, like 10,000-ish years or something like that for return period, which is pretty high. But the second method will sort of bring that into, bring it into focus a little bit more. Okay, so if you wanted for a specific point in space, this is a way to estimate the return periods. Okay, and you can also do it with greater than or equal to some EF number or something like that too. This example was for specific EF2 winds, which are like 37 to 48 meters per second or something like that. So within that range. Okay, the second method is this spatially based method. Okay, so that was the first method. The second one is where things get a little interesting. Okay, so now we're going to write this, at least I'm going to write it in blue. We're talking about sort of a new method. Okay, for large buildings and really infrastructure. And we'll briefly talk about it, but think about something like transmission lines. Okay, they span maybe hundreds of kilometers. Okay, the chances of some point along that line being impacted by a tornado is pretty high. Okay, so this is how some methods how you would account for these things. Okay, so for large buildings infrastructure, okay, typically a union between the building and tornado is considered. Okay, for example, okay, so let's say you have some large building. Okay, in the example, what I'll do above, let's say I'll make it really large. Okay, but let's say now we have these tornadoes, okay, that impact the building. Okay, can be from a number of different places. Okay, so here, okay, this is our origin point for the tornado. Okay, for everywhere. But all these, both of these tornadoes, okay, would be considered, okay, hits on the building. So basically, it doesn't matter that only a portion of the building was impacted. Okay, so basically you assume that any point on the building is impacted. Okay, and there are a couple different references on that. So, and they're generally older for tornado risk. Okay, Twisdale and Dunn, 1983. And then Garcon et al., 1975, cover a little bit about how to deal with spatially based risk. Okay, and we'll describe these. So let's go back up and say now, let's say within this region, we have some building that sits within this region. And let's say this building area is 1 square kilometer. Okay, it's large, probably big warehouses and things like that are probably 1/10 of that area. But for the example, okay, we can think about some very large structure that sits in this region. Okay, and so now this area, EF area, okay, is going to be a combination of a bunch of different things, okay, which we'll define. Okay, where W and L are tornado width and length. A and B are the building plan dimensions. Okay, so let's say this is B and this is A. And then H and G are the projected dimensions of the building. Okay, so now you got a bunch of different things that you need to consider. So this area is not just the tornado area. Okay, basically what you're going to create is and we'll write it down and I'll show an image here. Okay, an expected damage origin area. Okay, and this is basically a locus of tornado origin points that would strike your building. Okay, so basically you need to find, you know, how many different, basically just an area that encompasses all these tornado origin points that would hit your building. So I show an image of that. Okay, that's what I showed. Here's an example from the Garcon reference. Okay, basically you have some building size, you have some tornado width and length. Okay, and then basically this sort of area that is in black here are the locations or all the tornado origin area. So if a tornado starts within that black box, it would damage your structure of interest. Okay. So now instead of just the tornado width and length, now you have the building size to be concerned with. You have and all the dimensions associated with that. Let's see, 15 minutes. I get to the ranking vortex. Well, long. We get there. Okay. We'll try to get this done. Okay. So for an example, okay, let's look at a simple example where the tornado sort of moves at direction perpendicular to the building. Okay, so we have our building area here. Okay, we have and really these are sort of the length and widths are really sort of expected tornado width and length. Okay, so this is the expected damage origin area. Okay, so the tornadoes are really expected values on length and width. So for example, okay, it's going to look like this. So this area will look something like this. So for example, again, this is the bounds of the tornado origin point. So for example, this distance here to here and on the other side is the width of the expected width of the tornado over 2. Okay, so if the tornado started here, that expected width would reach, half the width would reach the outskirts of the building. Okay, and the same with the other side. Okay, so remember the origin points were basically halfway in the damage width. Okay, so this is the width over 2. Okay, let's say now this is the tornado length here and here. Okay, and so if you multiplied both of these areas here in the shaded region, okay, this would just give you the width times the length. Obviously, if a tornado started on top of the building, okay, you need to consider that area as well. Okay, the area inside here is going to be height of the building. Well, let's get the projected area here. So also then you have the building projected area on this side. Okay, so if this was the average length that reaches to the end of the building, you need to go back that dimension, which is G. Okay, and this projected height is H. Okay, so you have this area here too, which is H times L. Bless you. Wait, what did I do here? Yeah. And then these two areas, which is W times G. Okay, so let me give you some dimensions here. So let's assume that the length of the building, or sorry, the length of the tornado and width of the tornado is 2 and 0.2. The dimensions of the building, B and A, are 5 kilometers and 0.2 kilometers. And then H and G are just the projected dimensions here. They're equal to the building dimension in this case. Now, the projections could be different if the tornado comes from a different angle, but here we're just kind of doing a simplified exercise. Okay, so if we did this, now the return period for the spatial dimension estimate is something like this. So now it's the area of EF, which includes all these extra dimensions. Okay, times this lambda, which I'll explain in a second, over then the area of the region, okay, to the -1. Okay, and now lambda is the number of tornadoes per year, where here V is equal to some EF number that you're interested in, okay? And so let's say for our example, there are 0.9 tornadoes per year where EF2 winds are encountered. Uh-oh. Okay, let's try this. I've frozen up. Okay, sorry, we have a question from the online group too. So asked that, can you please clarify what the 2,800 year value represents? So that was in the point-based example. Is it return period of at least one EF2 event occurring somewhere within the 1,000 kilometer study area? So yes, so it's, yeah, similar to that. So it's really sort of the expected length of time where any point within that 1,000 kilometer study area would be affected by EF2 winds. Okay, so yeah, I think it's probably the same thing what you're asking, but yes, that is correct. So at any point you would expect, yeah, okay, good. All right, so in the interest of time, I've got to get to the ranking vortex. That's the last, that's in your homework. So, okay. So let's just go through the calculation here. I won't step through it. If you calculate the area of the EF here, this is much larger, 2.44 kilometers squared. If you calculate then the return period, 2.44 is your area times your tornado rate over your region to the -1. Okay, you get a return period of about 455 years. Okay, so here, if you're looking at a building that has 1 kilometer squared area, okay, you have a return period that's about 5 times more likely if you have a large structure. Okay, so this is the difference. If you're thinking about, again, probability based on like a town or some large area, hospital, something like that, that has a large campus, okay, that probability goes up just because if you count any portion of that area being impacted by a certain wind speed, okay, that return period is going to go up when you include all the possible locations where that tornado could occur from. Okay, any questions? Any questions on that? Let's go back and rework it. Okay. One other thing, so that's really for sort of rectangular structures. Another thing that generally are considered are things like line structures, for example, like transmission lines, right? They really only have, I mean, the individual structure has dimension, but if you're looking at the line, it really only has one dimension, which is in the direction of the line. So you could have some transmission line, looks like this. You have structures sort of scattered throughout. Okay, now the area that you would consider, if this was the length of your transmission line, okay, really the area that you consider looks like this, where the area is the length of the line times the expected length of your event. Okay, so L is transmission line length. Okay, and then this other L is the expected path length. Okay, and this is the case, can be the same case for downbursts also. Okay, so that area value that you use in the calculation then is just a product of the length of the line times sort of the average expected length of the event. Okay, so you can see then where that probability would go way up if any portion along that line were to be impacted. And to show you some examples of that, a couple different ones. Okay, ASCE, and we'll talk about this when we talk about codes. These are the tornado wind speed maps, and I mentioned it. Okay, includes the plan area of the structure. Okay, so this is for 929 square meters. If you go in there, as the area, the plan area goes up, those wind speeds also go up. Okay, because then your return period then reduces for larger effective plan areas. Okay, here's another example. This is in the US. Okay, so this is for large warehouse buildings. This is a whole nother issue that we're really just talking about frequency and intensity at this point. Okay, we have a lot of warehouse building type collapses in the US from tornadoes. Here's an example near St. Louis and not too far from Champaign in Illinois in 2021, where you have sort of a partial collapse of the structure due to tornado loads. And part of the reason that they get hit fairly frequently is they have a large footprint. Okay, sometimes, you know, around a tenth of a square kilometer even. So very large warehouse buildings. And if they get hit, the loading part, they're very susceptible to failure, which we'll touch upon hopefully tomorrow. Okay. I don't want to go past the time. I'll tell you what, maybe, so what we'll do is, so for the homework, you can attempt it. It deals with the Rankine vortex. You can look at that code and see what the model looks like. We'll finish the model part of it tomorrow. We'll derive it. We'll talk about that. It should take 15 minutes or so. And then we'll move on to topic 3. Okay. So I'll give you a reprieve on the homework too. So maybe by Thursday at the end of the day, you can turn it in, since we're not going to cover the Rankine vortex still tomorrow. Okay. Thank you. Thanks for your patience.